You know, a little while ago I went out and I got myself a Montreal smoked meat sandwich and it was delicious. And as they were making it, they asked me what I wanted on it. Well, more meat, really. But I said, well, I could better have some mustard on there and maybe some of those cucumber slices, put a few of those jalapenos down. And then they asked if I want it toasted. Well, of course I want it toasted. But at that point, two things happened. Number one, I started waiting and waiting. And the lineup behind me got a little bit bigger and the people got a little bit more patient. But the second thing that happened was I realized that in this sandwich, there's some really important chemistry. Now you might be wondering what I mean by that, important chemistry in a sandwich. And I'm not talking about preservatives and the mustard, although mustard oil is a really fascinating thing. I'm talking about reaction mechanisms. Now before we get into reaction mechanisms, let's start talking about a sandwich mechanism. A sandwich mechanism. How do I make a sandwich? Well, everybody knows how to make a sandwich, but let's break it down to the steps. I would butter a piece of bread and I would put that to the side. I would take mustard and put it on another piece of bread and put that to the side. And then I would take my bottom piece of bread and I'd pile the meat on top of it, pile it high on top of it. And then I would take the top piece of bread and I'd put it on top of that. Now I left out the jalapenos and the cucumbers, and I get that, I understand that, but just work with me here. Now at this point there's a few things that are kind of important that I want you to notice. Number one is that some of the pieces that we made, some of the things that we produced in this process, we ended up using later on. So the bottom piece, we don't have it at the end of it, it's part of the sandwich. The top piece, same thing. The middle, same thing. What we have is, when we're done, is we've gotten rid of all these little things that we produced in the middle. Let's call them sandwich intermediates, and that term makes a little bit more sense later. But sandwich intermediates, now when we're all finished and we take what's left over on that we needed to have to begin with, and what do we make? We end up with a sandwich, a fairly basic sandwich, but if it's Montreal smoked meat, it's still going to be delicious. Now, how does that apply to chemistry? Yeah, we're getting there. What we need to understand about chemical reactions, because that's what we're talking about, is that very few chemical reactions happen in a single step. In the same way you can't make a sandwich all at once, you have to do it in individual steps. Same is going to be true for chemical reactions. They, like sandwiches, are going to be a series of smaller steps that when you're done with the steps, you're going to have the overall reaction. And the products of some of those steps, the things that you produce in one step, you're going to be using as reactants later on, and those are going to be called reaction intermediates. And reaction intermediates you will not see at the end. Well, how do you know that they're there? Good question. We'll talk about it later. Now, what I need you to keep track of is that, by the way, you don't need to write this down. I just want you to follow the logic. I want you to see what's going on. But here's some possibilities of reactions that happen. You can have a reaction that is unimolecular. So in this case, the molecule just breaks apart. Maybe it had to hit the side of the container, maybe it bumped into another molecule but didn't actually react with that molecule. All you need is that molecule to hit something and it breaks. If you were to study that reaction, you find out that the rate law looks like that. In other words, the rate only depends on that ozone, the O3. Makes sense, I hope. You could take a reaction that is bimolecular, two molecules, and those two things collide, end of story. And there's some reactions that do that. Some reactions that look like they should do that don't do that. But that involves a collision of two molecules, and if you were to study that particular reaction, you would find out that the rate depends on that the nitrogen monoxide and the O3, ozone, equally. Now mathematically that should make sense. Now here's where we're going to blow some minds. Is that when we're talking about a reaction like this, the rate law does follow the balanced chemical reaction. How do we know that? Lots of experience, but also if I were to look at a more generic case, and I didn't find an actual reaction, but where one molecule collides with another molecule of the same kind. So let's say an oxygen atom with an oxygen atom to make an oxygen molecule. The rate law would follow the concentration of oxygen atoms to the exponent 2 eventually. So if I were to look at the reaction of two oxygen atoms making one oxygen molecule, hey, the balanced chemical equation and the rate law connect. Now I know you're trained to ignore that, but when we get to this level, because now we're talking about reactions at the molecular level, not overall, now it actually starts to work. because we're talking about an elementary step. Now, an elementary step is a reaction at the molecular level. What are the molecules that are actually reacting and colliding? Not the overall thing. It's going to involve one molecule reacting, or two molecules, or very, very rarely three. So for our purposes, one or two is going to be what we work with. The overall reaction then comes from the series of elementary steps combined together. Now, by the way, elementary step, elementary reaction, elementary process is another term. They all mean the same thing. Now, there is actually two more things on top of this. Okay, number one is that the rate of the overall reaction is going to be determined by the slowest step. So my sandwich, doesn't matter how fast they buttered it, doesn't matter how fast they piled the meat on it, doesn't matter how fast they put it together, stop, slow down when we were cooking it. Making more butterers come out, or getting the people to butter as fast as possible, won't help because of the toaster. Now, if you had more toasters or a bigger toaster, you could put more sandwiches on at a time, more people could get through the line. So, slowest step dictates the overall speed. We're going to call that, in chemistry, we're going to call that the rate determining step. And that is going to tell us a lot of information about our rate law. Or our rate law is going to tell us a lot of information about the rate determining step. It's going to work both ways. Second thing is, like I just hinted at, the rate law reflects the rate determining step, where now, when a reaction mechanism, balanced chemical equation, because it's going to be really small, and it might just be 1 and 1, at the absolute most it's going to be 2 and 1, balancing numbers, that will bump into the rate law quite nicely. So, how do we get a reaction mechanism? Well, a reaction mechanism is the series of steps. We already know that. Second thing is, it's an educated guess, which means we'll never know for certain. But there are some ways to make our guess more educated. And that involves making sure that the step, we limit it to 1 or 2 molecules colliding at a time. And the second thing is that if we know our rate law, we can use that to pick out our rate determining step. And then I suppose there's a few other things, but a lot of that's going to come with practice. All right, so here's an example just to work through. We don't really, well, just follow the logic. So let's try and get through it quickly. So you can see the reaction. Somebody's proposed the following mechanism. Now you'll always see it saying proposed, but okay, propose the following mechanism. And the mechanism they propose looks like that. Okay, well, how do we know if it's right? We will never know if it's right. How do we know if it's reasonable? That's a better question. Well, one of the things to look for is, do we get the overall reaction? If I cancel out the reaction intermediates, and there's not many on this case, but if I cancel out the reaction intermediates, do I get the overall reaction? Yes. So that means that proposed mechanism is reasonable. There's a couple of other things that I can use. Number one is if I know the actual observed rate, and we know how to determine the rate. Trial 1, trial 2, trial 3, change concentrations, off we go. Now, I didn't give you this before, but if I'll give it to you now, and you were given the rate law for that reaction, can I go back and reevaluate my mechanism? Because what does this tell me? This tells me a couple things. It tells me that there's a reaction, an elementary step, that involves only those two things, one of each. It also means that that step is the rate determining step, although that may or may not help us decide if the mechanism is reasonable. So let's go back and have a look at the mechanism. The mechanism that was proposed had, as the first step, 1 nitrogen dioxide, 1 fluorine. It reflected the rate law, or the rate law reflects, or is reflected in the rate determining step, or in that first step. All right, let's look at an example, and we'll try that one. So please do write this one down if you didn't write the previous one. So here's a reaction. You may need to pause to write it down, and going to give you a observed rate law, because a rate law is something that we can observe. Trial 1, trial 2, trial 3, increase concentration, away we go. All right, so my rate law looks like that. Your job then is to propose a mechanism. Now we're going to do it together, so don't worry about it. Or don't panic, I should say. Worry about it maybe, but don't panic about it. So here's my solution, or here's our solution. As I work through the solution, what I need to keep in mind? I need to keep in mind that the rate determining step is going to be reflected in the elementary step and in the rate law. They have to kind of look alike. And for this one, that means the rate determining step is only going to have nitrogen dioxide because that was the only thing in the rate law. Okay. Because of the exponent 2, that means that there's going to be 2 of them. And then the elementary steps have to add up to the overall reaction. That's the other thing I have to keep in mind. If I know those 2 things, then I should be able to come up with a reasonable mechanism. So here's a step. And you'll notice what I did. Let me back that up a second. My first step was, or tried to be, the rate determining step based on the rate law. And then I bring in the other stuff that I need. Now here's the weird thing about this one is that my reaction intermediates, it's kind of one of those weird things because I produced it and I reacted, but how would I have known that? From the rate law. Okay, my rate law said I needed 2 nitrogen dioxides, even though my final overall reaction, there's only 1. Okay. Isn't that cool? Then I can also label one as slow and the other one as fast. Now, do I have to label slow and fast? Often I will, simply so that it shows that I know more about that reaction. Here's another example. And again, please write this one down, pause it if you need to, and away we go. So here I've got one reactant making 2 products, so it's a decomposition reaction, but my balanced chemical equation says that there's 2 of them, and my rate law says that. Now, the overall reaction says that I need 2 of those things, 2 reactants, but my rate law says only 1. That means that if I look at this mechanism, you'll notice that the mechanism only has 1, and it just decomposes on its own. So it's one of those unimolecular deals. And then the other one comes in the next step. If you were asked to identify the rate determining step, what would you do? You'd look at the rate law, and then you compare that to the proposed mechanism, and you say which one looks most, or which one matches up the best. So because our rate law only had 1 of those reactants, then I'm looking for the step that only has 1 of those reactants, and by the way, not the other one. So I could label it like that. First one is slow, second one is fast. Now there's a couple questions that should pop up in your mind. Based on the examples that we've had so far, one of the questions is there always only 2 steps? All of the examples we've had so far have been 2 steps. 2 things to keep in mind. Number 1, no. Number 2, for where we're at right now, 2 steps is pretty reasonable. Not exclusive, but it's a pretty reasonable place for us to start learning about reaction mechanisms. But here's an example of a case where there's actually 3. And we could go through and we could cancel out the reaction intermediates, and we would end up with an overall reaction that looked like that. So 3 steps. Could it be more? For sure. Does it matter? No, we'd still be doing the same thing. Second question that might pop up in your mind, is it always slow step followed by fast step? Now you have to know the answer to this one is going to be no. Because 2 reasons. Number 1, chemistry is far more bigger than that. Number 2 is whenever people start asking these questions, they're kind of looking for the shortcuts, right? How do I not think and just label? I'm going to give you an example. You don't need to write the example down, but when you're looking at the example, what I want you to do is I want you to track the rate law and rate determining step in the mechanism. So here's an example. The rate law is given there, and it looks a little bit more complicated, but not completely weird from things that we've done before. We've done it where exponent of 2, exponent of 1. Okay, so now we're talking about a 3rd order overall. Wow, what would that mechanism look like? Well, the proposed mechanism for this reaction is actually much more simple than you may have first expected, but it's fast reaction first, slow reaction second. In other words, you have to always use your head. You can't slip it into neutral and coast. Really, really important. Now, as an introduction to reaction mechanisms, that's it. I don't know what you want to do with your time from now on. We're going to work with this in class. But for me, I'm hungry. I got to get a sandwich. Let's see. We got data retrieval, decals, decorating, dancers, dehumidified, delicatessens. Perfect. Talk to you in class.